Before going to the new section, 2.5, I would like to finish section 2.4. There is some topic that I wanted to cover. And it is called the derivatives as a rate of change. So suppose, so it's in some sense, this is application of our derivative, physics application. So suppose you have particle that moves according to the equation S equals to t plus 1, where S is a distance, and t is time, and we want some constants, of course. So if we graph, this is the linear function, and its graph look like this. So it goes through when t is 0, so this is my t time as distance. So when t is 0, I get 1, and when time is minus 1/2, it is 0. So my line looks like this. No. So we can calculate the slope of this line, and we remember that the straight lines are the special case. These are the functions, the linear functions that have the constant slope. The slope is the same for all points whenever I calculate them. So I say this is the formula for the slope if you have a linear function, and if you substitute these 2 points, so this point is 0, 1, and this point is minus 1/2, 0. So this is my say y2. Okay, this is say p1. This is p2. My points. So y2 is 0. Y1 is 1. Then x2 is minus 1/2, and x1 is 0. So I get minus 1 divided by minus 1/2, which is 2. So my slope is 2, and we know that the graph has some physical interpretation. It shows if you choose the time, you can find the distance that the particle has traveled. But what about the slope? Does it have any physical interpretation? And it turns out that yes, because suppose we measure our our distance in meters and our time in seconds. So then, so my y as measure, my y is s is a distance, so it measures in meters, and my x is time in measures in seconds. So my slope will be then 2 meters divided by 1 second. And so in other words, if s changed by 2 meters, whenever t changes by 1 second. So the rate of change of s with respect to 2 is 2 meters per second, which is just the definition of the velocity. So in case when the particle is moving, when the equation of the when the equation of your distance is linear, so when your distance depends on time linear, then you have a straight line and the slope has the meaning of the velocity. But of course, in a natural life, in the real life, we do not travel with a constant speed. If you look at our speedometer, then the needle is moving from 0 to 50 miles per hour, and then when we stop, it goes to 0. Then when we accelerate, it can go up to 100 and so on. And it turns out that if you plot the graph of our distance and time, it will not be a straight line. It will look something like that. It's not straight line, but some curvy. And what we can say in this case when we have not a straight line, but something more general. In some intuition says that instead of calculating the slope, because there is, in some sense, there is no slope of the nonlinear function, but what we can do, we can calculate the slope of the tangent line. So at some given point, it's not. Make it more like this. So at some point t, say t0, we can calculate the slope of our tangent line to the curve s of t. And in some sense, it will tell us what is the velocity at that moment. So this is my change in s, and this is my change in t. And so what is the slope? Let's recall that the slope of the tangent line to the curve y equals f of x is called the derivative f prime of x. And so that means that our instant speed at time t is just, so it's the slope of the tangent line, but if you have if our distance is described by equation s of t, by the function s of t, then instant speed will be the derivative of that function. So here's an example. So suppose you have your particle moves along a line according to the function s equals t square, where s is measuring in feet and t in seconds. Then, of course, we can calculate our derivative, ds over dt, and we did similar stuff last time, so I'll skip the steps, the 3 steps to calculate the derivative. So I'll just write the final answer. It is 2t. And actually, that's what we'll do today in easier way. And how can we interpret that? We can interpret that velocity, so this is how does the velocity depend on the time t. So that means that, for example, t equals 2, our velocity will be 2 times 2, 4 feet per second. And for example, for t equals, say, 5, our velocity will be 2 times 5, which is 10 feet per second. So again, comparing to the compare with the linear equation, s equals, for example, that's what we started, 2t plus 1. The derivative of s, again, you can calculate and see that it is just 2. So that means that at t equals 2, my velocity is just 2 because it doesn't depend on t. At time at 5 seconds, my velocity is still 2. So that's another interpretation of the constant slope. So your velocity is not changing during the time, while if you travel according not to a linear function, but some quadratic or maybe more different, more complicated equation, then your velocity will depend on time. And the very last comment, that the difference quotient that appeared in our previous class, delta y over delta x, which is the same as this one, is called average rate of change of y with respect to x. While f prime of x, which is the same stuff, but with the limit when delta x goes to 0, is called instantaneous rate of change. Sorry. Instantaneous rate of change. Again, of y with respect to x. So, and that's, maybe you have heard about that in physics. There is average speed, there is instant speed, and that's where it came from in some sense, the difference. So in one case you consider it without limit, in another case you consider the limit. And in the linear case, when you have just some linear function, these two are the same, of course. But in more general situation, it is different. And let's start chapter 2.5, derivatives of polynomial. And in some sense, we will come back to the instantaneous rates of change in chapter 2.6 and discuss other applications to physics and etc. Derivatives of polynomials. Okay, let's start with a very simple function. F of x equals c, where c is constant. What we can say about the derivative of such function? So let's recall what are the steps. First, we need to calculate delta y, which is f of x plus delta x minus f of x. But this function doesn't depend on x, so just c in first case and c in second case. So it is just 0. Then we calculate delta y over delta x, which is 0 divided by delta x, and this is just 0. And the third is to consider limit of delta y divided by delta x when delta x goes to 0. But this is the same as limit of 0, which is just 0 itself. And so what we get that derivative of the constant function is equal to 0. Okay, let me specify that where c is constant. So this is kind of trivial polynomial in some sense, the constant function. And what if we consider next case, for example, f of x equals x? What is derivative of this function? It is not very complicated. You can do it again using the definition of the derivatives, but also you can think about this as a straight line with a slope that equals 1. But as we discussed, the derivative is the same as a slope of the tangent line, but in case of the linear function, this is the same as the slope itself. So that means that derivative of x is just 1. And now let's consider the general case. What if, and this is kind of theorem that says that if you consider the function f of x equals x to the power n, where n is some positive integer, then derivative of this power function is equal to n times x to the power n minus 1. So let's prove it. Let's first consider some. I mean, last time we even did something similar when we had polynomial x cubed with something. But in general case, what you need is what is called binomial theorem. And binomial theorem says how you open the parentheses like this, a plus b to the power n. We know the formula for n equals 2, right? that is a square plus 2ab plus b square. And we know what happens with a plus b cube, which is a cube plus 3a square b plus 3ab square plus b cube. But what about a plus b to the power 4, say? And it turns out that there is such formula. There is such formula, and in fact, it is equal to a to the power 4 plus 4a cubed b plus 6a square b square plus 4a b cubed plus b to the power 4. But the question is how to calculate. You can guess what is the pattern of the powers. So their sum should be equal to 4. But the question is, what are the coefficients? And this binomial theorem says the following, that a plus b to the power n is equal to a to the power n plus power n minus 1 times b plus n times n minus 1 divided by 2 factorial a n minus 2b squared and plus so on, and plus what? Plus b to the power n. So this is factorial, if you forgot, and factorial is equal to product of consequent numbers below n. So it's 1 times 2 times 3 times so on times n. So for example, for factorial will be what? Will be 1 times 2 times 3 times 4, which is 6 times 4, which is 24. And so on. But what we actually need is just first two terms, because let's try to apply this binomial theorem that you, by the way, can also find inside front cover of the book. There is a formula how to calculate a plus b to the power n. But let's apply it in our case. So what do we have? We want to calculate how to apply this to calculate derivative of our power function. So what is the first step again? We should calculate delta y, which is again f of x plus delta x minus f of x. And if I substitute, what I'll get x plus delta x to the power n minus x to the power n. And you see that indeed we have sum of two functions to the power n. So we have exactly the same, we have the same situation where we can apply binomial theorem. And so let's do that. So I just write binomial theorem where my a is x and my b is delta x. And so what I'll get x to the power n plus n x to the power n minus 1 delta x plus n minus 1 divided by 2 factorial x to the power n minus 2 delta x square plus so on plus plus so on delta x to the power n. This is my first term. I just open the power and minus xn. And as we discussed last time, that in general, when you consider the derivative, you should see some cancellation. And it's true in this case. So xn and xn are cancelled. And what I get is the following. it is n xn minus 1 delta x minus 1 and minus 2 divided by 2 factorial xn minus 2 delta x square plus so on plus delta x to the power n. This is first step. We just consider the change in y. Next step is consider the ratio delta y over delta x. And this will be what? I just divide term by term. So if I divide this guy, I will get n x to the power n minus 1. Then I'll get, this is just some constants, n minus 2 divided by 2 factorial, xn minus 2, and delta x squared divided by delta x gives me just delta x. And so on, and plus delta x to the power n divided by delta x gives me delta x to the power n minus 1. So what is crucial that all terms except the first one, they contain delta x. So this one has just delta x. Next term will contain delta x squared, and next one will contain delta x cubed, and so on. And the last one contains delta x to the power n minus 1 even. And this is important because on the next step we consider limit when delta x goes to 0 of our ratio, and this is the same as this limit. N xn minus 1 plus again this long function expression delta x plus some other terms plus delta x to the power n minus 1. But again, I can use the property of the limit. The limit of the sum is the same as the sum of the limits. And because of this delta x, this term will go to 0. Second term contains delta x squared, so it also goes to 0, and all other terms. And the final one also goes to 0. And what is left is just the first term that doesn't contain delta x, and it gives me the final answer. And that's what I was looking for. That's what I wanted to prove. Okay. For example, we can calculate derivative of x cubed. So, of course, we can, let me do it once so you understand what is the proof of the theorem using delta, just the definition of the derivative. So delta y will be x plus delta x cube minus x cube, which is what I wrote down before, x cube plus 3x squared delta x plus 3x delta x squared plus delta x cube minus x cube. There are some cancellations. Then delta y over delta x, easy to calculate. I get 3x squared plus 3x delta x plus delta x cube. And the final limit, delta x goes to 0 of delta y over delta x. This is the same as this limit. 3x squared plus 3x delta x plus delta x squared. And this goes to 0, this goes to 0, and I get that it is 3x squared. But now, this is what I should do before, but now I have my theorem, and so I can just write something like this. So I have this, and I want to calculate this derivative. And so how do I do that? I put the power in front of my function. So I just, first I write 3, and then multiply by x to the power which is 1 less than the initial one, 3 minus 1. And that gives me 3x squared. Maybe put here to put. And that's how you can remember that. So when we differentiate, we decrease our power by 1 and put the initial power in front of our function. Okay, so you see that how compact the second option is. So instead of writing 3 steps and calculating some limits, calculating some, I don't know, binomial formulas, we just just one line. Let's prove another few important formulas. The following theorem that says that derivative of the sum of two functions is the sum of derivatives. Let me write in this notation, and during the proof we'll use other notations as well. So derivative of the sum equals to the sum of derivatives. That's how you can remember that. So let's prove it. So consider two functions. First one is f of x and v is g of x. And if you want to differentiate them, they both should be differentiable. And we discussed what does it mean. And let's try to calculate the derivative of the sum. So by the definition, I should consider the following ratio. So first, in the numerator, I write the delta y, which is f of x plus delta x minus g of, okay, let me put it here. Minus g of x plus delta x. This is my f, I don't know how to call it. Okay, let's call it capital F is f of x plus g of x. And we want to calculate f prime, right? So this is my capital F at point x plus delta x. And then I subtract f of x and g of x. Let me put it like that, which is just my capital F at point x. And then I need to divide by delta x. So this is just the definition, how I can calculate it. But let's recombine the numerator. So I will combine it in the following way: f of x plus delta x minus f of x, and then I have, yeah, here should be plus g of x plus g of x plus delta x minus g of x. And I again can divide term by term, so I can split it into two fractions like that. So I have this expression. But again, by the definition, by the property of the definition, it is the same as two limits of the first fraction, quotient plus limit of the second one. When delta x goes to 0. But since my initial functions f of g, f and g are differentiable, this gives me just the derivative of f itself at point x. And so I started with the derivative of the sum, or maybe it's better to write down in this way, df over dx. This is dg over dx. So I started with d over dx of the sum, and I got that it is d over dx of f plus d over dx of g. And if I come back to my u and v functions, if I want, then I'll get d over dx of u plus v is equal to d over dx of u plus d over dx of v. It's just different notations. And that's basically the proof. But let's do it slightly in different way. So second way, second proof. It just uses different notations that will be helpful further. So what we can do, we can say that delta u, which is the same as delta of f, it is f of x plus delta x minus f of x, and delta v, which is the same as delta g, is g of x plus delta x minus g of x. Then what we have? And our capital F is u plus v. Then delta what is delta f? Yeah, if we do it more accurately, what is delta? What I want to say? Yes, delta f will be what? Delta u plus delta v. So the difference is just delta u plus delta v. But then delta f over delta x will be delta u plus delta v divided by delta x, which is delta u over delta x plus delta v over delta x. And finally, limit of this when delta x goes to 0 is the limit of delta u over delta x plus limit of delta v over delta x. So basically we did the same story, but this is more compact notations using deltas, and in some sense it's better. When delta x goes to 0, when delta x goes to 0. But this is the derivative of u, this is derivative of v, and this is derivative of f. So we got, but f is u plus v. So it's just again another way to prove it. And there is another theorem. So this is the end of the proof. And there is another theorem that is an exercise 27. And it says the following, that d over dx of c times u is equal to c times du over dx, where c is some constant. So that means that you can put constant outside of the derivative. It's not difficult to prove, and that's why it's an exercise. But now we have powerful tools. So first we can this theorem, another theorem is about sum. Of course, from the first theorem, let's call it first theorem. This is a second. You can deduce that derivative of the difference f minus g is equal to difference of the derivatives. Because you just can consider g tilde, which is minus g, and repeat the same steps. Nothing will be changed. So let's calculate something interesting. So not very interesting, but something new, 3x to the power 4. So we are interested in the derivative of this function. So first, we are interested in derivative of 3x to the power 4. So first, by theorem 2, I have constant 3, which can be put outside. So it's 3 times x to the power 4 prime. But then I know how to differentiate x to the power n. In this case, x to the power 4. So it's 3 times, and derivative of x to the power 4, again, you put 4 in front of the function, then you multiply by x to the power, which is 1 less than initial one. And finally, you get 3 times 4 times x to the power 3, which is 12x to the power 3. 12x cubed. And this is the final answer. So again, very nice, because I don't need to consider 3 steps or whatever. So this is just warm up in some sense, because now we can differentiate a very complicated function in some sense, which is polynomial 5x to the power 4 minus 3x to the power 3 plus x2 minus x plus 10. So it's long expression, but again, what we can do. First, because the sum, again, using theorem 1, if you have, and you repeat it several times, so for example, if you have sum of 3 functions, of course, it is the derivative of that. That is sum of the derivatives of these 3 functions. And it's true for any numbers of the functions. And how to prove it? You can just say that this is my first function f, and h my second function, and use theorem first time, and get that this is theorem by theorem 1 is equal to this. And then again by theorem 1 you can say that this is this plus this. Again theorem 1. And you can repeat it as many times as you want. Okay, maybe tricky step, but if you think a little bit on it, it's not that bad. Okay. And what is the conclusion? The conclusion is that y prime I can write it in the following way. So it's 5x to the power 4 derivative minus 3x cube derivative plus x square derivative minus x derivative plus 10 derivative. So I just use the theorem 1 several times and obtain that when I have sum or difference, I can get just the sum or difference of the derivatives. And now I can differentiate each term. So first one, again, there is constant 5 in front of that, and I can put it outside. Then I differentiate x to the power 4. So this is theorem 2. But we know how to differentiate x to the power 4. It is 4 times x to the power 4 minus 1, which is 3. The same story happens with the second term. So by theorem 2, I can put 3 in front. So it's 3 times. And then I multiply by the power 3 and x to the power 3 minus 1, which is 2. Okay, let me do it into 2 steps again. 3 times derivative of x cubed, which is 3 times 3x squared. This is just our theorem for the power function, so it's just 2 to the power x. This we calculated separately, just 1, and the derivative of the constant function, which is 10, is equal to 0. That's what we started with. Let me recall that. We started that, where is it? Here, derivative of the constant is 0, derivative of x itself, it's 1. And now I just need to combine the results. So it is 5 times 4, 20x cubed, minus 9x squared, plus 2x, minus 1, plus 0, which is just 0. Okay, and this is the final answer. This is the most complicated example that you can get in this section. The rest is not that bad. But remember that sometimes you're confused with some constants, like pi is still a constant. Square root of 3 is constant. No. 1 over 2 is constant, and so on. That means that derivative of pi is still 0. Derivative of square root of 3 is 0. Even it looks like some function, or maybe, I don't know, irrational number, but it doesn't matter. It's just some constant. So the derivative of the constant is 0. How doesn't depend how ugly it is. Okay. This is kind of remark. Oh. Okay. And yeah, now let's return to the last thing that we covered last time, tangent line. So recall that what we started even with slope of the tangent line to the curve y equals f of x at the point x equals a is equal to the derivative evaluated at that point. And so let's do an example. Y equals x squared minus 2x minus 4, say. And we want find the equation of the tangent line at the point x equals, say, 3, for example. So what we need to do? We need to calculate. So in general, let me make the algorithm. So suppose you have y equals f of x and tangent line at x equals a. You're interested in. And so first, you need to calculate derivative of the equation of your function. Then you should evaluate it at the given point, and that will be m, which is slope of the tangent line. Third step is to write down the equation for the straight line in the following form. That's what we discussed at the end of the class. It is y minus y0 is equal to m times x minus x0, where x0, y0 belongs to y equals f of x. And basically that's it. So geometrically, it looks like this. So you have some curve like this, and you want to find tangent line at point A. Yes, but usually you choose this point. Usually, okay, this is kind of remark. Usually, no, not usually, always, sorry. Sorry. So you know that this line goes through the point through this point P that has coordinates A and f of A. So your y0, so this is just the general formula for the straight line, where x0 is A and y0 is f of A. So this is the last step, and sometimes you maybe express y. So now you have just put y to the right side, so you get that y is equal to m x minus x0, which is A, plus f of A. So this is kind of the final formula. Quite complicated, but it's not that bad when you try it on the examples. So let's come back to our example, y equals x squared minus 4x plus 2, and x at the point x equals 3. 2x, what? 2x minus 4. Right. So first step is to calculate the derivative. So y prime is, again, I can use derivative of the sum is sum of the derivatives, theorem 1. So that gives me x squared derivative minus 2x derivative minus 4 derivative. First gives me just 2 times x by the rule that we discussed. Second one, I can put 2 in front, and then I get derivative of x, which is just 1. And the last one gives me 0 because 4 is a constant function. So I get 2x minus 1. So this is, let me do another remark, that what we get, that y prime is 2x minus 1, which is slope, again, of the tangent line. And you see that the slope depends on x. That means that the slope is changing, and that's what you should expect, because if you have function like this, then the slope, say, function like this, for example, then the slope here, so if you draw the tangent line, is like this, point x1. But at point, say, x2, your slope is, your tangent line looks very different, and that the slope is also different. So we see again that the slope depends on x, comparing to the straight lines where it's constant all the time. Okay. This is first step, and just remark again. Second step is to evaluate my derivative at the given point y prime, and I'm interested at point 3. Y prime at 3 is equal to 2 times 3 minus 1, which is 5. So I specify the point, and I can calculate the corresponding slope of the tangent line. So even the slope depends on x, that means that you have many different tangent lines, but when you specify the point, you will get only one tangent line and only one slope for that. So don't stop on this function. It's not the final answer for the slope. You should evaluate it at the specific point that is given. And that is also kind of common mistake that I have seen. Okay, this is my slope m. Okay, and the next step is to calculate. So my x is 3, my y is x squared minus 2x minus 4. So my y at the point, so I need f of 3 for my function. So f of 3 is 3 squared minus 2 times 3 minus 4, which is 9 minus 6 minus 4, which is minus 1. And the formula says that the tangent line, so you have a line that goes through so tangent line is a straight line that goes through the point that with coordinates 3, -1 with slope that is equal to 5. And when you know such information, you know the slope of the line and you know the point that belongs to that line, you can write that equation that we discussed. So it's y minus y of 0 equals m times x minus x0. This is my x0, this is my y0. By the coincidence, it's not coincidence, but f of x0. So I have y minus y0, which is -1, is equal to m, which is 5 times x minus x0, x0, which is 3. And I can simplify it, so y plus 1 is equal to 5x minus 15, and y equals 5x minus 16. This is so. This is, I think, the most compact answer that you can get. Okay, so this is the equation of the tangent line. At x equals 3. Okay. Oh, yeah, thank you. You're right. I forgot to multiply by 2, indeed. 2x minus 2, 2x minus 2. So my y will be 4. Yeah, thank you. And so my m is 4. So here I have 4. Yeah, good catch. 4, which is now 4x minus 12. And that gives me 4x minus 13. So what if I have the same, what was x squared minus 2x minus 4? What if I'm interested at the tangent line at point x equals 0? So the same graph, but now I'm interested in a different point. So still y prime is equal to 2x minus 2, and my y prime at point 0 will be thus minus 2. I just briefly recall the steps. And second, y of 0 will be minus 4. So that means that my line goes through the point 0, minus 4. And again, I can apply that to this general form, which is m times x minus x0, x0. So it is y minus 4 is equal to minus 2 times what? Minus 2 times x minus 0. So I get that y plus 4 is equal to minus 2x. So y is equal to minus 2x minus 4. So what I wanted to say one more time, that we get completely different tangent line. So I just change the point where I'm calculating the tangent line, and you see that these two lines are completely different. And in fact, you can see it even on the graph. So y is equal to, again, x squared minus 2x minus 4. if you complete the square, it will be what? It is x minus 1 squared minus 5. Right, I get x squared minus 2x plus 1 minus 5, which is minus 4. And you can draw this graph. It looks like this. Looks like this. Come on. Not here, sorry. What I wanted. Okay. So it shifted to the right. Say here 1, 1, 2, 3, 4, 5. So what? This is 4. This is. So the graph looks like this. This is minus 5. And this is minus 4, minus 3, and so on. This is minus 1. So this is a graph of my function. And so first time I was interested in the equation of the tangent line at x equals 3. So it is somewhere 1, 2, 3. It is here. And it looks like that. While second time I was interested at 0. And so the 0 point was here. And the tangent line looked like that. So again, the equation of tangent line depends on the point where you want to calculate it. So they are different. And the final thing that I wanted to say today is about normal to the curve. So a line is called normal to the curve if to the curve, say y equals f of x at point x1, y1, if it is perpendicular to the tangent line. The tangent line through that point. Through that point x1, y1. So how to see it? This is the definition, of course, but why it's called normal. So suppose you have some function like that, and here's you're interested in this point, x1. So you draw your tangent line. This is tangent. And the normal then will be the line that goes through the point x1 and is perpendicular to your tangent line. And the point is that if this is the fact from the geometry, that if you have one line is, say, k x plus b, and another one, so slope k, and another one is, say, mx plus b, no, not plus b, but some, say c, doesn't matter. So the slope is m. Then they are perpendicular to each other. If m times x is equal to -1. It's not difficult to check, and it's nice exercise, not straightforward, but nice. For example, y equals x. If you consider this function, y equals x, and y equals -x, so slope is 1, and here slope is -1. There, the product will be, of course, -1, and that's what we see on the picture. So this is my y equals x, and this is my y equals -x, and they are perpendicular, of course. And so there is similar problem to find the normal to the curve at the given point. So you have some function at point x1, y1, and the solution of this problem is the same as for tangent line, but now the slope is 1 over derivative of that point x. Okay, let's call it x naught. Right. So before we learned that the slope of the tangent line is the derivative, and now the slope of the normal is 1 over the derivative at that point. And the other steps are the same. And here is minus that I forgot. Okay, thank you. Have a good day.